Hi everyone, and this is 2.1, adding non-collinear vectors. So we're going to start by just learning how to draw angles, vectors on an angle, and the steps start off with a suitable scale. We've done this before. So for instance, if I was given a vector in kilometers or meters, I can't possibly fit that onto a piece of paper, so I'm going to convert it into a number of centimeters. For instance, if I had 10 kilometers, 1 centimeter equals 1 kilometer, that means I would make a 10 centimeter line on my page or an arrow on my page. Next thing I have to do is draw a compass, northeast, southwest, and then I'm going to start measuring. So I start measuring the angle from the first direction towards the second direction using a protractor. We're going to talk about angles in a moment. You'll see all this come together. And the last thing I have to draw is the resultant displacement at the correct angle with the appropriate length. So let's put it all together. I'm going to draw a displacement of 25 meters north, 35 degrees west. So here's my setup. I've got my vector of 25 meters, and an appropriate scale might be something like 1 centimeter represents every 5 meters. And to check to make sure this scale is going to work, all I can do, I'll just do it over at the bottom here. If I take my 25 meters that I'm trying to represent and I divide it by my 5 meters, that's going to give me the number 5, which is telling me how many centimeters that vector will be on my page. So if you just divide by whatever you think is going to work, it'll tell you whether it will work. So 5 centimeters is pretty reasonable. So again, I've got my pieces in place. I've got my scale, I've got my compass. Over here, I've drawn what's called crosshairs. This just gives us a place to actually measure these angles, because if I kind of try to measure it in space with nothing to start and stop from, it's a little bit tricky. So I have to go from north to west, and so when I look at this vector, so because our vector is northwest, that means that there's our north and there's our west. Our vector is going to be in this area in some regard. So now we want to hold our protractor so that north is where we start measuring from. So we're going to align our protractor so north runs along the 0 mark. Now we're going to go from the north 35 degrees towards the west. I'm going to freehand it, but you would normally use sort of a ruler here. That's about 35 degrees. And now we want our vector to be 5 centimeters long. So again, using your ruler, I'm just freehanding it. That would be our vector. So it would be 25 meters. That's how it would be represented. And then this area here is our 35 degrees. So we've done collinear vectors. That's when we're walking back and forth along the same path, so right and left, or forwards, backwards, north, south. Non-collinear vectors is when we start making turns. So we might walk straight and then make a right turn. That would be non-collinear vectors. We're still going to use a scale method, a scale diagram method, and we're still going to add one vector after another, tip to tail. So very similar to when we drew them in 1.1. The steps here, we're going to start with our scale and compass. We've done that before. We're going to draw the first vector to scale, then add the next vector where we stop drawing the first one, etc., until we're out of vectors. Then we're going to draw the resultant vector or the resultant displacement from where you started to where you finished. Again, that's the same thing we were doing earlier when we did 1.1. It's like when you walk, you would walk, let's say, 10 paces forward. You wouldn't jump back and then start walking again. You would continue walking from wherever you stopped. So there are times where you won't have to make a scale diagram. So if it says make a scale diagram and solve this problem, you're going to get marks for solving that scale diagram. But if they don't ask you for one, still make a sketch, because these problems are very visual. So with a sketch, that will help you make sure you get the right direction in the end. When we're solving for that resultant displacement, we are going to end up with a right angle triangle. So imagine if we go north and then east, and then our resultant displacement is from where we start to where we stop, going in that direction. So we have both, if this is my delta dr, my resultant displacement, we have both a length to that line and we have an angle to that line. So a little bit of math to figure this out. The first one is our length. We're going to use c squared equals a squared plus b squared. And then to solve for the angle, we'll use our tan theta is equal to opposite over adjacent. Then we'll put the two pieces together to write our delta dr. Let's try an example. So a truck drives 34 kilometers north, then 16 kilometers west. What is the truck's resultant displacement? So these are our vectors, and let's start with our compass and our scale. So I would say that 1 centimeter should probably equal maybe 4 kilometers here. And again, we'll put north, east, south, west. Let's work out how many centimeters our vector should be. So our 34 kilometers will be represented by an 8.5 centimeter arrow going up, and then our 16 kilometer vector will be represented by a 4 centimeter vector going to the left. So I'm going to freehand again because it's hard to use a ruler on my touchscreen, but you should be using a ruler. So we're going to start with our northerly one, and we're going to go about 8.5 centimeters up. That's pretty good for freehand, actually. So that one is 8.5. Oops, you know what? Don't do that. We're going to put in the actual value, so 34 kilometers. And then we're going west, so we're going to the left. And we're, again, tail to tip, so we're going this way. That's a 4 centimeter line, but it is representing 16 kilometers. So our resultant displacement, what we're trying to solve for here, is from where we started, again, this should all be rulers, to where we ended. So we're going to call that one delta dr. And that's the one we want to solve for. So we're going to do our c squared equals a squared plus b squared to solve for the length, and then we'll use our tan theta to solve for the angle, and then we'll put it all together. So let's do length first. So we've got our 16 squared plus our 34 squared, and we're going to square and then square them both, add them, and then remember to get c by itself, we'll have to take the square root because c is also squared. I'm going to do that math now. So when I get it all together, I'm going to get 38 kilometers, and I'm going to keep it to 2 significant digits based on my digits there. And now let's do our tan theta. So the angle that we need is tan theta. Tan theta is opposite over adjacent. You'll notice that when I drew my resultant displacement, we want to know where that angle is at the base of the arrow, where it's aimed. So it's the angle here that I'm looking for that I've just identified. So the opposite is the 16 kilometers, and the adjacent is the 44 kilometers. And again, when I want theta by itself, that means I have to take 16 divided by 34, and then tan to the -1. That's probably a second function button in your calculator. Try it now and you can compare your answer with mine. So I'm going to get 25 degrees here, again maintaining 2 significant digits. So I'm not quite done yet. I have to put everything all together. So this is my final answer then. Delta dr equals 38 kilometers. I'm going to make my bracket for my degrees to go in, and then I'm going to look at my picture and decide what are the 2 degrees, which side am I measuring from. So you'll notice in the picture I'm measuring from the straight up and down, I'm measuring from the north, and I'm going towards the west. So that is my final answer, 38 kilometers north, 25 degrees west. The next part of the question asks me, what is the truck's speed and what is the truck's velocity? So let's bring over what we need for each of those parts of the problem. So we can see the equations are very similar. Ones are wearing these little arrows and ones are not, but that changes the numbers that we're going to use. For speed on the left, we need the total distance. So we've gone 50 kilometers. This problem, I forgot to give you a time, so I'm going to give you one now. Delta t we're going to say is 0.85 hours. So let's solve for speed now that we have everything we need. So v is going to be 50 kilometers divided by 0.85, 85 hours. We're going to bring it to 2 significant digits, so 59 kilometers over hours, which we can write as per hour. On the velocity side, we need displacement. Well, thank you, doorbell. We need displacement, so our displacement is what we just solved for recently. Again, we're going to use that same time that I just gave you, 0.85 hours, and let's solve. So v is equal to our 38 kilometers. You're going to put everything in here because all of it is important to our problem, divided by 0.85 hours. Let's see what we get. So I'm getting 40, we're going to take it down to two significant digits, so 45 kilometers over hours or per hour. And again, I put that direction in there on purpose because I want to make sure I recognize that I have to keep it, otherwise it's not a vector. So velocity and speed, you can see, are different values. This one you're going to try on your own first, so I'm going to read it, then you're going to pause, then you're going to look at the solution. So a car drives 13 kilometers south, then 8 kilometers east, then 2.5 kilometers north. What is the resultant displacement of the car? Pause now. So we'll start with our scale and our compass as usual, so we'll do 1 centimeter equals to probably 1 kilometer. You could do probably 2 kilometers, but you might get a little short on that last vector. And then we've got our north, east, south, west, and then we start drawing. So we're going to go south. Again, I'm going to freehand. You're going to use a ruler. We're going to go south 13 kilometers. So let's just do 13 centimeters. Again, that's not awesome, but you get the picture. There's our 13 kilometers for D1. And then we're going to go east for 8 kilometers. Again, you're going to, oh, that's really short. Let's try that one again. That's better. Delta D2, 8.0 kilometers. And then we're going to go north for 2.5. That's probably the best one of them all. 2.5. All right. And then, again, my resultant displacement is from where I start to where I end. So I'm going in this direction, and I want to know where it's being aimed. So this one's a little bit different because the right angle triangle actually is here. And so I have to be cognizant of the fact that this is still 8 kilometers in my triangle if I want to use my c squared equals a squared plus b squared. But I also have chopped the length there. So the whole length on the left was 13. I chopped 2.5 off, so I've got 10.5 kilometers represented here now. So those are the values I'm going to use, my green values, to make my right angle triangle, and now I can do my math. So I'm going to start with my c squared equals a squared plus b squared, and that's going to be for my length, as we know. So I've got my 10.5 squared plus my 8 squared. I'm going to find the value, and then I'm going to square root it again because I need to find the value of c alone. I'm going to bring my value to two significant digits, so I've got 13 kilometers. And now I'm going to find the angle, so tan theta, opposite over adjacent. So my opposite is 8 here, opposite my angle, and my adjacent is 10. Remember how I work this out? I just want theta, so I'm going to take my 8 divided by my 10.5, and then second function tan, and that gives me 37 degrees. So my final answer is just putting it all together now. So let's put it down here, delta dr equals 13 kilometers. My angle is 37. Now if I look at the picture, I can see that the straight angle is from the south and it's going towards the east. So there's my final answer. So let's try the speed and the velocity now once again, and I've just put the time in there because I forgot to put it onto your original slide. So we're going to use 0.40 hours in both cases. Let's set it up. So for speed, we need total distance. So we have 13 kilometers, then 8 kilometers, and then 2.5 kilometers. Oops, there we go. Remember, when adding, we're limited by lowest number of decimal places. So I have lowest number as being no decimal places. So I get 23.5. I'm going to have to round that to 24 kilometers there. My delta t was 0.40. So my v is 24 kilometers divided by 0.4. Let's see what we get. 24 divided by 0.4 equals 60 kilometers per hour. Now, here's a question. Is that the correct significant digits? Hopefully you're saying no, because this is showing one significant digit. Because a zero like this does not count. Only if I give it to you like this would it count. But a calculated value, because of rounding, doesn't count. So I would like to keep 2 significant digits, because if I look up here, my values are in 2 significant digits, which means I'm going to put that 0 to the right of a decimal. A little bit of scientific notation. A little bit of a pain, but that's the way it goes. All right, let's have a look at velocity next. Remember, our velocity is going to be displacement over time, and our displacement is our resultant displacement, and we just worked that out. And our time is the same. And when we substitute, again, we're going to substitute everything in, units, direction, all that good stuff, so that we can see what the units and the direction should look like at the end. So we're getting 32.5. Again, we're going to round to 33 for 2 significant digits. We're going to keep the units and the direction here. That should actually, I should put that in red, but that's our final answer. So now it's time for you to get some homework done. Boo, I know. But practice makes perfect, so practice, practice, practice. We'll be having a quiz on this next week, so we want to make sure we know what we're doing.